All right. So the book in chapter 5 kind of describes some of this stuff, but what I wanted to talk about is why we use the mole. So atoms are really, really small. They're a lot smaller than light waves are. And so, hang on just a second. Uh, okay, we can't possibly count them. And if we had anything that we could see, there would be more atoms than we could possibly count in a lifetime. Um, so what we do is we use a bigger number, and the mole is a great big whole giant mess of atoms. And it has a specific number, and there's a history as to where this comes from. Um, but this number down here, 6.022 times 10 to the 23rd, that is equal to 1 mole. And it's also called Avogadro's number. But it's just a number. So you can think of it like a dozen is equal to 12. So you can have a dozen eggs, and you know in your head, well, that's not really 1 egg, that's 12 eggs. And then, people sometimes use the term a gross, which is 144. Well, this is what we use in chemistry. And the way it works out is really nice because it turns the mass of one atom into the mass of 1 mole, but with units of grams. And so that's why we use that kind of weird looking number. So to give you a sense of how big it is, I'm putting some numbers here. So over on the side, I have 57,000, which I looked up was about the population of Scott County last year. So that's everybody in Scott County. And then this is the population of the United States, 328 million. So obviously when we're in the millions, that's a big number. But of course, more people would be the number of people on the planet. And so now we're talking 7.8 billion. So that's a pretty big number. And then our national debt is in the trillions. So this is $19 trillion. So those are really, really big numbers, unimaginably big numbers. This is a mole. So, with all of those zeros, it's almost twice as long as the trillion number. So really, this is just a huge, huge, huge number. And so you might think, oh, well, if we have such a huge number, then this has got to be a lot of stuff. But if we're looking at 1 mole of water molecules, so this number of water molecules, it's about a third of a cup. So it's about 18 milliliters. So that's not very much, water at all. And so that just goes to show you how small atoms are and why we need to work with something so big. Now, this number here, the 6.02 times 10 to the 23rd, is not a number that we usually use in chemistry because we never work with atoms or molecules. We always work with moles. So a lot of times in like high school chemistry classes, they'll have you translate back and forth, do the calculation to convert back and forth between them. And I have one assignment where I have you do that calculation, but for the most part, we just never use this number because we're always working in moles. So if you compare them, like I said, you can, it works out nicely for us that if we're working in molecules, the mass of a molecule is in a unit called an atomic mass unit, an AMU. So water is 18.02 AMUs. But an AMU isn't something that I would like weigh myself in. So it's kind of hard to understand what that is. If I have a mole of water, it weighs 18.02 grams. And so using the moles allows us to work in grams, which is a size we can understand. So molecules are too small to measure, but moles are in volumes and masses that can be easily measured in the lab, and that's why we use them. So in order to convert from one to another, and I have I have a presentation that I'm going to put on later today that goes between the, that shows how to do conversions if that's something you struggle with. But what we would do is we remember that carbon on the periodic table weighs 12.01 grams. So that means 1 mole of carbon is equal to 12.01 grams. And so we're going to use that equivalence to create a ratio. So when we convert, what we do is we take what we know. So this question says how many moles are in 50 grams? So what we know is 50 grams. We start with that, and then we multiply by a ratio between the units that we want. And so we want to get rid of grams. So we're going to put the grams on the bottom, and we want to go to moles. So we're going to put moles on top. And so this is what it looks like. We have the 50 grams, and then we multiply by this ratio, which looks like a fraction. We have the units we don't want on the bottom, grams. The units we do want on the top is moles. And then when I have the same units on top and bottom, like I do for 50 grams and 12 grams, I can cancel those out. So I can get rid of the grams. And so I'm just left with the moles. So when I multiply this all out, I end up with 4.16 moles. So one thing that's good to remember is that when you're multiplying by a fraction, what that means is you multiply by the things that are on top and you divide by the things that are on the bottom. So sometimes when you're looking at a fraction, it's easy to forget that what you're really looking at is a division problem. And if that's something that you're going to struggle with, I'll direct you towards the content I'll put on later that'll go more step by step with converting. So then the other thing we can do is go in the opposite direction. So if I said how many grams are equal to 0.167 moles, then I would start with the measured amount here, the 0.167 moles, and then I would multiply by a ratio again, but I don't want the ratio in the same direction because I want to get rid of moles. So I'm going to put the 1 mole on the bottom and the 12.01 grams on top. So this is what it will look like. So in order to get rid of the moles, I have 1 mole that's just regular on top and 1 mole that's on the bottom. So those cancel out. And then I'm going to multiply the numbers across the top. And then whenever you divide by 1, you get the same thing back again. So it just turns out to be 2.00. So that would be how you get from grams to moles and moles to grams. Now we're not going to do a whole lot of that. I'll probably ask you to go between those two things, but the chapter gets a little bit into what's called stoichiometry, and the book is going to go into more detail on this part than I am. So I'm going to show you the basic stoichiometry first, and then we can look at the stuff that would involve these mole to mass conversions. So what stoichiometry is, aside from a big scary word, is it's how we use the chemical reaction to figure out amounts. So it's kind of like if you're looking at a recipe and you are not going to just make that recipe once, you're making for a great big catering business thing instead of just for your family, you have to scale up your recipe. And so we would use stoichiometry to figure out, okay, how many of these ingredients do I need, or how much of the product will I get? And so the way we do that is we look at the balanced equation. So chapter 4 goes through balancing the chemical equations. And so this middle area here is where we have that balanced equation. And then what we do is we pay attention to the coefficients that are in front, and we have to keep those ratios the same. So just like if you had 2 cups of flour and half a cup of sugar, then you would need to keep that ratio the same when you're scaling the recipe up. We need to do the same thing with the sodium hydroxide and the chlorine. We have to keep those ratios the same. So what this chemical equation says, if we think about it in terms of molecules, is that if I have 3 molecules of chlorine, I can make 1 molecule of sodium chlorate. That's what this NaClO3 is. But remember that whenever we use moles, we can use it as if we're using the word molecules. We're just saying a bigger number. So we could also say it takes 3 moles of Cl2 to make 1 mole of NaClO3. So whether we talk in molecules or moles, that ratio stays exactly the same. And so even if we can't remember the number 6.02 times 10 to the 23rd or how to convert back and forth, it's okay, because all we need to know is that that ratio is the same. To keep the ratio the same, then if I want 9 moles of the sodium chlorate, well, that's 9 times as much as 1. Then I need 9 times as much of the chlorine. So I would need 3 times 9, which is 27. So that's kind of the idea of stoichiometry. But of course, we never work with these nice, simple whole numbers. So here's an example of what we might do if we had decimals. So if we had a question, how many moles of chlorine are required to make 3.8 moles of sodium chlorate? We'd start with the measured amount, and that's this 3.8 moles. So that's how much was measured as what we want. And we're going to put that in the first part of our equation. And then we're going to multiply the ratio of the coefficients. So we're going to put the thing we want to get rid of, the sodium chlorate, is going to go on the bottom. And the thing that we're looking for is going to go on top, the chlorine. And then these numbers 1 and 3 come from the chemical reaction. So this 1 comes from the sodium chlorate here. Now it looks like there's nothing there. Sometimes I'll say in chemistry, 1s are invisible. So if we have something and we write it there, then that means there's at least one of them, and we only change the number if it's not 1. So this is a 1 next to the sodium chlorate, and then next to the chlorine, here's my arrow, is a 3, and so that's why we put the 3 there. So we just say 3.8 moles of sodium chlorate times 3 moles of chlorine divided by 1 mole of sodium chlorate. And so this mole of sodium chlorate and mole of sodium chlorate, one is on top, one is on bottom, so they're going to cancel out, and I'm going to be left with 11.4 moles of chlorine. And I'm sorry that everything's so squished together there. My equation editor wouldn't let me put spaces in, so I had to kind of run everything together. So this kind of ratio is what's in chapter 3. And they spend some time talking about how to make these ratios and how you can do them in either direction. And then to do the conversion, you just need to know that the one that goes on the bottom is the one that you already know the amount of, and the one that goes on top is the one that you want to know the amount of. So we can do, this one has coefficients on both of them. So if we have sodium chloride and sodium hydroxide, the sodium hydroxide is this first chemical, and it has a coefficient of 6. And the sodium chloride has a coefficient of 5, so it's over here. And so the question says, how many moles of sodium chloride will result from 1.5 moles of sodium hydroxide? So what we know, the measured amount, is the 1.5 moles of sodium hydroxide. So that's what's going to start out here at the beginning of our equation. And then we're going to multiply by the ratio. So I always start with what goes on the bottom because that's the thing I know. I'm going to put the moles of sodium hydroxide down on the bottom, and I'm going to put moles of sodium chloride on top because that's what I want. And then these two numbers, the 5 and the 6, they come from this chemical equation. So there's a 5 next to the NaCl, so I'm going to put a 5 on top. There's a 6 next to the NaOH, so I'm going to put a 6 on the bottom. And then I'm going to multiply, so I multiply across the top, 1.5 times 5. And then remembering that this fraction is a division, I'm going to divide by that 6 on the bottom. And then I end up with 1.25 moles of NaCl, or sodium chloride. All right, and then in chapter 3, they go through several of these types of problems, and you'll have one homework assignment. I think it's called mole to mole conversion, or just moles to moles. And it's basically setting up this type of problem. Okay, so in chapter 5, they throw in a new twist. And that's because we don't really have an instrument in lab that measures moles. I can measure grams if I put things on a balance, and I can measure volume, I can measure milliliters if I put things in a graduated cylinder, but I don't have anything that measures moles. So a lot of times we'll start with grams and we'll say, well, what if I had 5.9 grams of sodium hydroxide instead of 6 moles of sodium hydroxide? How does that change things? And so what you would do is you say, okay, I know how to go between moles and grams. So your first step would be to change that mass to moles, which was the first part of what we did today. And then you would change the moles of sodium hydroxide to the moles of sodium chloride, just like we did on the previous slide. And then you would say, now that I have moles of sodium chloride, you're going to get to grams of sodium chloride, again, doing what we did at the beginning. So this part that was in chapter 3 is kind of the middle part of a more complicated stoichiometry problem. Now, I won't ask you about this on any quizzes or tests, but I will probably have a homework assignment that asks you to do it one time just to let you give it a try. But if you get it, don't stress over it because it's not going to appear on a test or a quiz. I'm more interested that you understand the concepts of what we're talking about than being able to go through all of the mathematical detail, because you're not going to need to do that. That's not a practical skill. All right, so any questions about this? I think this is my last slide on this. Let me double check. Yeah, that was my last slide.